We'll be talking with Max Tegmark, who is a renowned cosmologist and in his spare time is a proponent of the many worlds interpretation of quantum mechanics. And that says that if quantum mechanics says there's more than one outcome of any action, then it will happen in worlds other than the one we're aware of. Do I have that roughly right?
In this universe, you have it right.
You can't count the ones in which I have it wrong. And Bill Phillips is a quantum physicist who you could say is working in the trenches. He manipulates atoms so that they can be used for different applications, like atomic clocks. And in 1997, he won the Nobel Prize for his work. David Albert is a philosopher. David Albert is a philosopher who was also a physicist himself, and he is renowned for his insights into the thorny philosophical questions raised by quantum mechanics. And Brian Greene, as you know, works on string theory, and it's an effort to bring quantum mechanics and gravity together, something I've always longed for myself. We don't see the billions of microbes on our arms. I mean, there are a lot of parts of our reality that's invisible to us. It might have an effect on us. We might get sick from them, but we don't see them except with instrumentation. We don't see, except lately in the last century or so, we don't see outside of the range of light that we're adapted to. And it affects us. We're affected by ultraviolet rays and that kind of thing. But we don't pay attention to it most of the time. Is it possible that the quantum world exists and may, not only affect us, but we are it, but we're not adapted to paying attention to it? Maybe it's with your machines and your theories. You can see it, and we can't. And we somehow need to bridge that gap. I mean, just take this first thing. Brian was showing us on the screen the two-slit experiment with the waves. So this whole idea of a probability wave, when these electrons are fired, they're single electrons, right? And they're fired. So let me ask Max, you're the expert closest his hand to me right this minute.
Yeah.
We think of that now as a probability wave. Is that a real thing, or is that a mathematical construct?
Well, the most important thing you're going to learn tonight is that even today, a century after this theory was first pioneered, you get experts on stage who will disagree passionately about the answer to this. I'm chosen to be the fall guy here, I think, the minority who thinks that the probabilities are just an illusion. And let me explain why. I think that what seems to us as random is really not random, and it has to do with cloning. So let's forget for a moment all about quantum physics, and let's sedate you. You go to sleep, and while you're sleeping, I'm going to use some nanotechnology.
Wait, I think some people in the audience are already there.
That guy in the back. And
you're going to sedate me, and then
I'm going to measure where every atom in your body is and build a perfect copy. So we're going to have two Allens, and then I'm going to wake one of you up right here on stage, and the other Allen is going to wake up in Washington Square Park. Okay? And both of them are going to have exactly the same memories of this discussion, this sedation. Right? So if I ask you now, which of those two Allens are you going to be? If I ask you specifically, where are you going to wake up? Mm-hmm. You can't, it's going to seem, there's one Allen is going to feel he randomly woke up in Washington Square Park. The other one is going to feel he randomly woke up here. There's no way for you now to predict where you're going to wake up because both copies are going to wake up somewhere, right? And the parallel universe interpretation of quantum physics, which we're going to argue about, says exactly that's what's happening. You were effectively being cloned. It's not just the little particles that we're made of that can be in two places at once. Brian very nicely showed how an electron can go through two slits at the same time. But since we are made of these particles, we too can be in multiple places at the same time. And you can be here and in the park at the same time.
Okay, well, let me ask you a question about this before other people rush over and choke you.
Go for my jugular.
When you say that these particles, that the wave, the wave probability, the wave function, is not a real thing. Are you saying that these particles are splitting off and going into other worlds, or not? I mean, they're coming out of this electron gun and they're going through two slits. So what's happening? I mean, it didn't sound like you explained what was happening.
So,
not like you went into this other thing.
So the one thing we all agree about is how we should calculate the math. And the math just says there's this curve, which Brian showed nice plots of. Now, Brian called it a probability wave. That's where it gets contentious. Whether you interpret it as a probability or something else. Usually, so we don't fight so much, we have a different name for it. We call it the wave function.
Okay.
It's a curve.
Okay, so in other words, you're saying that it's not a probability.
It's just a mathematical thing. We all agree how to calculate it. And then Brian showed a beautiful animation of how this can spread out for little things, and he said that for big things, it doesn't spread out. But the problem is that Erwin Schrödinger pointed out that you can actually devise experiments where even this wave function for big things also spreads out. He pointed out that if you take a cat and then you build a horrible little device which kills the cat or not, depending on what just one atom does, then afterwards the whole cat is going to have very spread out one of these curves and be doing two very different things. So it turns out we can't confine this quantum weirdness to the micro world of the small. It spills out and causes all this wonderful confusion.
Well, as I said, they would explain it all to you. So now, what's your take on this?
Well, my take is very different from Max's. Max has a very interesting but not entirely orthodox view about this, and I fall into the more conventional and orthodox point of view, the same one that Niels Bohr took. And so to understand what my take is on this, let me just back up a little bit and talk about this two-slit experiment again, because it's a wonderful experiment. So you shoot an electron at these two slits, and what quantum mechanics tells us is there's no way that we can tell where that electron is going to end up. But it's going to end up someplace. When it hits the screen, it's going to make a flash of light, and we can tell where it is. But beforehand, there's no way of telling. If you shoot a gun, you can tell where the bullet's going to hit. But if you shoot an electron, you can't. Now, the problem is how to make sense of that if that electron is really a real object. And the way Max likes to make sense of it is that in one universe, it goes there, and in another universe, it goes there, and in another universe, it goes someplace else. And the way Niels Bohr makes sense of it is to say, you're not allowed to ask that kind of question. That's the orthodox point of view in quantum mechanics. Such a question is meaningless. The only thing that's meaningful is what is the result of the measurement. And so you can calculate what the probability distribution is, and we all agree on how to calculate. What we don't agree on is how to make sense of that, how to interpret the calculation, how to say, what does that calculation mean? So Max says the calculation means that there's this distribution of all these gazillion different worlds in which the different things happen. And my interpretation is, in the end, I measure something, and the probability of getting that result, and if I do it again, I'm going to get a different measurement, and after a great number of measurements that we saw illustrated on that video, it's going to build up exactly the probability distribution. So we like to call that interpretation the shut up and calculate interpretation, meaning all this stuff about many worlds, it doesn't matter. In the end, I know how to do the calculation. Max knows how to do the calculation. We get the same answer, and when we go into the lab, we get the same results. And whether I accept Max's result or whether I accept the shut up and calculate answer, I get the same answer. Now,
let me ask Dave Albert, because I sense you're treading on Dave Albert's toe a little bit. How do you feel about that? That if you just shut up and calculate, are you missing anything? Are you missing any of the fun in life?
Yeah. Yeah. It seems to me you're missing much of it. Probably all of us initially got interested in science because we wanted to know what was going on. So there ought to be a resistance. It's proper for there to be a resistance to to someone who tells you that there are certain sorts of questions you're just not supposed to ask. Nobody is born and opens their eyes with an intrinsic interest in how a particular experiment is going to come out or how to do a particular kind of calculation. The kind of interest we come to the world with, I think, is an interest in what's going on. And if it's really the case that there are certain questions about what's going on that it turns out to be inappropriate to ask, it seems to me right to regard that as an enormous disappointment of the whole scientific project. And so in this respect, in this very broad brush respect, I guess I'm closer to Max. I'm interested in trying to figure out what's going on, in trying to be able to tell a story of why it is that these experiments come out as they do, rather than just having a method which might as well be close your eyes and say abracadabra or something like that for calculating how they come out. I think that the particular story that Max is enthusiastic about is a story that seems to me to have a lot of problems. The problem isn't that it's wacky. It's pretty clear that the world is wacky. I think there's a useful distinction to be made here. It's pretty clear that the subatomic world is strange one way or another, no matter how you cut it. The important distinction is whether it's merely strange or whether it's strange in such a way as to make it literally unintelligible. Whether the world is stranger than we know or stranger than we can know, okay? The worry about the many worlds interpretation, I think, maybe I can be a little bit more concrete about this. The reason we have for believing in quantum mechanics in the first place, the hard evidence that we have that something in the neighborhood of quantum mechanics is true, has to do with observing statistics of repeated measurements on similar systems, okay? The kinds of experiments that Brian was talking about before. The worry about the many worlds interpretation is that it's not going to be able to account, since it's an interpretation that says everything happens for sure, it looks like it's going to be at a loss to account for why we observe these particular frequencies as opposed to those particular frequencies, why we observe these particular statistics of outcomes of measurements as opposed to those particular statistics of outcomes of measurements when we repeat a measurement a bunch of times. Because the many worlds interpretation says all of those statistics are going to occur for sure, okay? Here's a slightly different way to put the worry. Quantum mechanics has these probabilities at the bottom of it, which we've been talking about. And the reasons we have for thinking quantum mechanics is true are precisely that the kinds of statistics we observe when we do these experiments are the kinds of statistics that these probabilities say are the statistics we ought to expect.
Let me pick you up on that. Let me ask Brian, too, because that's a very interesting question. Those of us on the outside of this mysterious realm that you people study so assiduously, we hear about how it works on chance, and it sounds a little fuzzy to us. And yet, Brian, isn't there an accuracy in quantum mechanics that's amazing?
Yeah, I mean, quantum mechanics is the most accurate theory that has ever been written down by a long shot. But what it's accurate about is unfamiliar. Right? So it used to be in the time of Newton that if you want to know where a baseball will land, you use the laws that Newton wrote down, and they predict exactly where the ball will land. So that's the kind of data that you use to support Newton's view of the world. Quantum theory says that's just wrong-headed. Quantum theory says what you should be predicting are the likelihoods, the probabilities of the ball landing here or here or here. And if the math says that the ball will land 30% chance here, 30% chance here, and 40% chance here, then do the experiment 100 times And if it turns out that 30 times more or less it lands there, 30 times more or less it lands here, and 40 times more or less it lands there, then you're confirming the probabilistic predictions of the theory. Now, this example with a little ball is one particular one that I just cooked up in order to explain the basic idea. But when it comes to particles like electrons, you can do a quantum mechanical calculation of a property of the electron. Its magnetic properties. The details don't matter at all. The calculations are extraordinarily difficult. It took a group of physicists more than 30 years to do the calculations. But by the end of the calculation, they had a number that emerged from quantum mechanics, 2 point whatever, 10 decimal places long. They go out and they measure that particular magnetic property of the electron, and digit by digit by digit, 10 decimal places long, it agrees with the prediction. That tells you that you're on to something. It's unusual, but you're on to something.
Okay, so given that incredible degree of